have Joaquim Gomis visiting us from the University of Barcelona. Actually, he's at UT Austin right now, visiting Steven Weinberg for a period. But he's going to tell us about the canonical realization of BMS symmetry.
Thank you for the invitation. And I can say that essentially it's more than 20 years that I gave a seminar here. Therefore, time has passed very quickly. Okay, what I would like to discuss is about the canonical realization of BMS symmetry. This talk is based in some old paper by two Italians, Longhi and Materassi, FPH 9803 128. A more recent one of Longhi and myself, 1508 and there is some coming paper by one of my ex-students and a student, myself. Okay, probably you have heard a lot about BMS symmetry. I don't want to review the recent interests of BMS symmetry. I'm going to say the minimum. If we have time and you have questions after I explain my own work, we can return what other people apart us are doing. Because in a sense, we are doing something that is pedestrian, but I will say that is illustrative. And essentially, one of the things is something that we say to the students, that if we have an algebra, or we have we can have several representations of this algebra. In a sense, what I'm going to tell you is a representation of this algebra that it is different from the one that is standard. Now, let me say a few words about standard. And this started with BMS on the 60s. And essentially, the idea was to study the symmetries of asymptotically flat spaces. And this will be already a subject of one lecture or seminar. What I want to say is what they have in mind is the following. Well, by the way, I am going to use, in order to make the things more clear, the Penrose representation of the Minkowski space, where here we have square plus, here square minus, the past infinity, and here the future infinity. Okay, the idea of these guys was the following. Let's consider a flat Minkowski space-time with retarded coordinates. I will define in a moment these guys here. This, if I introduce the coordinate, retarded coordinate u equal to t minus r, and this is the round metric of the ground sphere, it results that this is the Minkowski spacetime, and they had gravitational part that has to do with information of, for example, incoming gravitational wave. I don't want to discuss this thing, but saying what they were looking. We know that the theory is invariant under diffeomorphism, and what they ask is which diffeomorphisms are going to preserve this sort of metric, where here pragmatic, and here we'll put something that for them was initially some wave that was propagated until this will be U, if you wish, and this is R. Okay. Therefore, what are these symmetries that preserve this thing here? And they were thinking that they are going to get, since we are considerably asymptotically space-time, that will have Poincaré, P mu, M mu nu. But they found much more than that. They found an infinite-dimensional algebra that we characterize. Okay, these are the translations and this is the rotation. They found some infinite set of translations called supertranslations, and in their case there was only Poincaré. And the property of these supertranslations is that as being translations commute, and it gave a basis of the Lorentz group. What I mean is that if we have M mu nu with PLM, in the same way that the Lorentz generators rotate the momenta, the Lorentz generator rotates this infinite set of momenta. Therefore, here we have something like it's PL prime, and here I put a matrix, an infinite dimensional matrix, M mu nu, L prime, M prime, Lm. That is what they found. And they found an explicit form of this matrix, and this is an infinite dimensional representation of the Lorentz group. By the way, this is the thought in 4 dimensions. What I'm going to take initially is also in 4 dimensions. Now, that is all history. Now, the recent interest for PMS symmetry has to do with Strominger in the 14th, essentially.
Excuse me.
Yes?
Is it possible to write down how the super translations act on these coordinates? I mean, what do they do?
We can find what is this matrix. Yes, there is a specific matrix that you can write.
Now, so if we have like Poincaré transformations, well, I mean, like shift, for example, I mean, we have translations, or we have...
No, okay, good. It's a good question. The point, it is this infinite set of momenta has associated infinite set of coordinates. In a sense, you are thinking if the transformations on the basis space, on the Minkowski space, will reproduce this, the whole thing. And obviously, it's not going to reproduce that sort of thing, but this doesn't mean, I mean, it's the transformation on the base do not generate the whole transformation. You will need to treat an infinite number of coordinates. By the way, as I will mention later, how these P mu are related to this one. It results that P00, P1M, okay, M01 minus 1. This essentially is the P mu, okay? Therefore, if you want to think in this term, we need an infinite number of coordinates, but that's not the thing that the people has been doing.
So
I was trying to say,
L and M take all the non-negative.
L and M has to do with the harmonic spherics, because here there is S2, and S2 naturally will have YLM. We will see
okay.
in the construction that sort of thing. Okay, essentially, he was interested in the S matrix of gravitational interaction, and he realized, I say only was because I cannot explain my own word, realized that the source theorem of Weinberg, that's again in the 60s can be related to the wide identities of this PLM, of the super translation. And technically there are interesting things to realize. That is how you glue. You have BMS symmetry plus BMS symmetry minus, and the point is how you glue here. There is a way, by the way, if you are interested in that, I recommend watch in YouTube the lectures by Strominger, 10 lectures by Strominger, where he's explaining his approach. I'm not going to do that. I'm going following Longhi. Longhi was one of my mentors when I was in Italy doing my PhD thesis in '69. He had a nice idea. For the first part of the paper, has something to do, has a lot to do with him. I mean, the idea is, can I find other representation? Here I have an algebra, there's an infinite dimensional matrix. Can I have another representations? And the answer will be yes. And in a sense, in a very trivial way. And the point is, let's consider a free Klein-Gordon field. Okay? We have this Klein-Gordon field, we have the corresponding Klein-Gordon equation, and we have an expansion and the solutions of our field. This is something that we could explain to the students. It will be, since, by the way, here we are in an hyperboloid, therefore we are going to have that k squared plus m squared will be equal to 0. Like that. And here we could put a of k, a kx, plus emission conjugate. I take real. I could take complex. This doesn't change at all. Now, and the measure here is the measure of the hyperboloid that essentially is d3k divided by 2p cube, the square root of k squared plus m squared. Okay? Now, we say to the students, that is the first example of a field theory that is Poincare invariant. Which are the generators? Okay, so we apply Noether theorem. And Noether theorem is telling that this is integral in d3x, t0 mu. Okay, and the t0 mu is expressed in terms of fields and momenta. And now, this is an off-shell expression, and now I go on shell. I use this expression here, and this results to be integral in d k tilde and the hyperboloid k mu a daga k a k. And analogously, we could find that m mu nu, I do the same thing. There is a pair on shell. There's a pair of shell and a pair on shell, and this essentially could be something of this term from here, k mu a of k mu partial k mu minus mu nu a daga. Okay, good. That is something that is well known. The main idea of Giorgio was the following thing. Can I generalize this guy here to infinite momenta? You should have an inspiration. You have that sort of thing, and you ask, do I have a way to put in here something that makes the role of the momenta? And as you will see, the answer is yes. But essentially, this is the key thing. You have your Poincare generators particular retranslations, and you are going to generalize from their expression. Therefore, it's clear that you should learn something, some intrinsic property of the form momenta, okay? And in doing that, let me tell you that we will arrive, that we will have a representation of this algebra, okay? In terms of this quantity here. Now, how are we going to do this? Okay, the point is we know that we are in a hyperboloid, and this hyperboloid, I call it Q. This is the hyperboloid, and we know that this has to do with Euclidean ADS3, by the way. Here we have this thing here, and we have this hyperboloid. As often we do when we are doing things with holography or with ADS, we introduce some embedding coordinates, Q's. It's clear that the metric with the Q's is a metric in momentum space, but still, I like. Okay? We have this thing here. Therefore, I am going to introduce some embedding coordinates and compute the induced metric on this curved space that is H3. It's an hyperboloic Euclidean three-dimensional space, and that is essentially it. If I take this embedding, and now I compute this square induced. And I have a formula. That's, again, something rather trivial. And we found the following thing, that delta J minus square root k squared plus m squared ki kj dki dkj. Okay, that's the metric of on this hyperboloid. Now we know that associated. This is it results that the curvature of this metric being is a constant negative curvature. That's the reason that is an Euclidean ADS3. We can compute what is the form of Laplacian, and the Laplacian has some form. By the way, could you tell me 10 minutes before? Okay. It results, if I use the ordinary formula, we have this nabla square 2m square k nabla m square k nabla square. I should say that nabla I it is partial with respect to ki. Okay. Therefore, let me summarize. It's I want to generalize form momenta, and form momenta obey a Rondeman shell. I have a metric on this one, and I can correspondingly construct the Laplace-Beltrami operator, and I could find the following thing. And here, if you wish, starts something that is rather. By the way, if I was using polar coordinates, I will do this many times. If I use polar coordinates for my k in polar, and I introduce r, maybe the notation is misleading because this r is not configuration R, but is in momenta, I introduce this quantity here. It will have the form, and maybe you will recognize, this is m squared dr squared 1 plus mr squared plus r squared ds2 of the S2 sphere. And this, you can recognize that with the Furter change to the parabolic cosine of rho, that's are the global coordinates, for example, in Euclidean ADS3. Okay, what I was trying to say is the following. Now, if for some reason you dream to compute what is the action of your Laplacian on your momenta, you find that this is an eigenvector, and the value, let me precise write this one here, it is precisely 3 k mu divided by m squared. Therefore, here, if you wish, it comes, at least to me, the surprise. If somebody has an intuitive idea why this should be this without doing the calculation, I will be happy to hear. But the point is, if I do that, what is, and pass to the other side, this is an intuitive operator D that is minus m squared, the Lambertian, plus 3. And what is the property of k mu? This is d of k mu is equal to 0. Therefore, it's a 0 vector. It's a 0 eigenstate. But now, if you look at this thing here, this is essentially considering what was done before. For example, in holography, Witten is considering what is the solutions of a Klein-Gordon field in an ADS background. And he's doing for some generic value of the mass, and here there is a special value. This 3 has to do with the dimensions. Therefore, what it suggests is that if you want to generalize that expression, what you should do is to look for the most general solution, the 0 mode, of this equation, of the Klein-Gordon equation in ADS with a special value for the mass. Okay, that's what it will substitute this thing here. Therefore, you ask yourself, D, this operator, what is the most general solution of this epsilon? And this, I solve this in polar coordinates. I do separation of variables, and we found the following thing. Write epsilon as some theta and phi 3. This part here is going to give me the harmonic spherics. On the part of R, there are two types of contributions, and here is something that I should explain. This, of course, also when we study holography, that we have two types of behaviors for our functions. And the point is the following. We are interested in what is the behavior, since we want to generalize k mu, we want to have the asymptotic behavior of k mu. This implies that k mu should be regular when k goes to 0. That implies when r goes to 0. Remember that r is this quantity here. Therefore, if you wish, here we want this non-singular. And that's the crucial thing. Let me comment that precisely in this situation here, I am in the infrared, if you Now, it results that the solution of this equation, it is R of R, it is R to L. L is the harmonic sphere is the one that is appearing here, but some hypergeometric function f to 1 with certain arguments that I am not going to write for you. Therefore, essentially, our solutions, this phi, can be labeled by omega Lm, and essentially it is this function R of L, let me use this one, by the harmonic spheres. That's the result. And that's analogous to what people have found in studying a particle in a curved radius. The only difference here has to do with this thing. Now, let me say the results, and let me later explain which nice properties has this object here. But once I have this, what should I do? I came to here and I'm saying, okay, what will be my PLM? My PLM will be dk tilde omega Lm a daga k a k. Therefore, that will be my my supermomenta. Okay.
But this is
A
in
question?
ADS, not in Minkowski. So is this ADS space you're working with or not?
Sorry, sir?
What's the space-time here that leads to this? Is it four-dimensional space-time?
Yes.
Oh, sorry.
Is four-dimensional? No, excuse me. Is four-dimensional space-time that is foliated with hyperbola.
Oh, I see. Okay.
But yes.
Do you need to say anything about the large R behavior of the solutions?
Yes, it results that it has the same property that if is 1, this is scales as R.
Oh, you wanted to ask. Okay,
Therefore, exactly the same behavior like that. It's really a generalization of my momentum. Now, essentially, this is the main idea. But the point is that these functions, what are the properties of these functions? And the result is that these functions, what they are, is an infinite dimensional representation of the Lorentz group. How do I see that? But if you wish this, okay, there are technical things to prove that sort of thing, but essentially, once I have this together with my mu nu, the algebra that I will have, it will close it, and it's the BMS algebra. So that's the result. One thing that I could say before going in knowing properties of this three-dimensional representation of the Lorentz group is that by construction, this PLM on the vacuum is going to be 0. And this is, in a sense, not in a sense, this is different from the approach of BMS gravitational, because there, what is the vacuum? It is the Minkowski space, and it results that the supertranslations are spontaneously broken. The Minkowski space breaks spontaneously the supertranslations. And associated to these ones, we have the soft photons, and that's the reason that in the ordinary approach, you will have, for example, theorems about soft photons where one soft photon scatters an ordinary type of matter. But here, physically, this is the main difference. Here we are having an unbroken realization of the BMS group. A question before I go in some explanation on this infinite dimensional representation. Okay. How do we construct this infinite dimensional representation? You see, it's something we could construct starting at the beginning with this equation here. We could do the following thing. We could ask ourselves, what is the action of P mu on my creation and annihilation operators? And this one is A k mu, A of k. Remember that this one here I am on the hyperboloid. And analogously, I can ask what is the Poisson bracket of M mu nu with A of k, the annihilation operator, and the results and differential operator d mu nu on AK. And this differential operator is written in the following way. For example, I write the form of us that is associated to d0i. It has this form here, is square root of k squared plus m squared partial with respect to k sub I. You see, it is a differential operator that works on the hyperboloid, therefore I have only three stuff here. Now, if I construct explicitly these operators, I can go and ask how they act on this one here, and let me write this for you, at least in one case. Okay. But maybe before saying that, you could check that omega 0, 0, omega 1, m, these are the expression in polar coordinates of our four momenta k mu. Therefore, and that's the only finite dimensional invariant subspace of the representation. Therefore, it's clear that in a way this omega Lm should reduce to that, and it results that they reduce. And for example, in order that you have an idea of how K3 is one of, okay, I have erased it, but no, it's there. You have this operator, and you ask yourself how this acts on this function here. Remember that R is K over M. Okay, this is a complicated thing, but there is some non-trivial coefficient that in fact one can check that this agrees with what Sachs in particular computed for the BMS in the 60s. You see here it's sort of rising thing, omega L plus 1m plus I2L plus 1, and here will be some coefficient that maybe omega L minus m. And I could write the action of the other generators, and this is has some matrix, some expression that is L minus m, L plus m divided by 2L minus 1, 2L plus 1. Therefore, you can check now the following thing, that if you compute the action of m mu nu PLM with this expression that I gave to you PLM prime, these objects here, what I have written here, are precisely the Sachs form of the BMS transformations. Therefore, the final result is that one is finding another representation of the BMS algebra that is with unbroken symmetry.
So this K3 is one of the boosts?
K3 is one of the boosts.
It's not one of the momentum.
Sorry?
It's not that K mu up there, it's actually the Ki further down. There. I'm getting confused between two Ks. That one and the one above.
Yes, it's the same.
Okay.
This is the boost, the action of boost in direction 3. And the boost on the direction 3 has this form of these differential operators, and you can compute and use properties of the hypergeometric function, blah, blah, blah. That's not a trivial thing. You can prove this thing here. You can realize that this is precisely the infinite dimensional matrix of Sachs that he was finding in the BMS study. Yes?
Are the indices on the hypergeometric function such that it truncates to a polynomial, or it doesn't?
No, does not truncate.
Okay.
If we go, okay, now that you said that, if we go through 3 dimensions, it's much easier. And if we go, for example, should tell you 2 things: how you do massless and how we go to 3 dimensions. Now, how we do massless thing? Remember, the idea was we had an hyperboloid, and we computed the induced metric, and from there the Laplacian. But if we are now massless, we are cones. The cone will have a singular metric, therefore I cannot compute the Laplacian. But still, you could do the following thing. You could write d was minus m squared delta plus 3. And in here, remember, was a factor 1 over m squared. There are factors of 1 over m squared that you could they cancel. Therefore, this it has a finite n0 limit. And this is the operator that you are going to use. Okay, I'm getting confused with my notes. And the operator results to be this d equal to m0 is 1 over r partial respect to r cubed partial respect to r plus 3. And in here, you also find that there are 2 types of solutions, one that will be regular and the other one that it will be non-regular. And the point is that in this case, it's much simpler. Omega Lm results to be r y Lm. Therefore, rather trivial in the massless case. Therefore, even that you cannot use directly, immediately the idea of the induced metric, there is a way out. By the way, for the ones of you that are amatori of group theory, you can prove that this operator here in this situation, or this operator here in this situation, is nothing more than the Casimir. You know that the Lorentz group has 2 Casimirs. And it results that this, the Casimir of the Lorentz group, the one that I am interested in is this one. Let me call this C2. It results that these operators are precisely proportional to this Casimir operator. Good. Therefore, that's how you do massless. And there is this important issue that this could be used, probably used in other situations for another groups. Sorry, for another spaces or for other space-time. Now, let me state how I go with time.
You find you still have 20 minutes.
Okay, let me, one moment to 3 dimensions, and I go mouse this. It results that the, I will concentrate in the massless case, but I will like to write also the operator D for the massive case, because there is a point that I would like to mention. Oh no, okay, let's see that. Dm equal to 0 results to be the following thing. Here, really, it is a very, very simple thing. Plus 2. You see, remember that here we have plus 3. Here we have plus 2. And this is the differential operator analogous to the one, this is in 4 dimensions, and this is in 3. But the point is that the solutions of that are rather trivial. We do again. We check that our momenta is an eigenvalue of this equation, and therefore we find the generalized expression, the omega L. This time, this will depend on R and theta only, because in 3 dimensions we will have here we have an S1 instead of S2, okay? And this omega L are particularly simple at R exponential I L theta with L belonging to the intercept. Therefore, in 3 dimensions, the corresponding PL will be dk omega of 2 plus 1 omega L ak. And in this case, the action of the Lorentz group in 2 plus 1 dimension, it is much simpler, and we have the following thing, that J, we have generators K plus K minus, the boost, and J, this being K1 plus IK minus IK2. J results to be on omega L, is L omega L, and K plus minus on omega L is really a later operator, is L minus plus 1 omega L plus minus 1. Therefore, in 3 dimensions, things are particularly simple, and you can find, okay, at the moment, in 3 dimensions, if I have time, and in 4 dimensions, the question is, in the same way that we have generalized the momenta, can I generalize the Lorentz rotation and construct superrotation? And the answer will be yes, or the answer is yes, but instead of doing that, I would like to comment in something that I think is interesting, and is the following. Can I realize this these symmetries, this super translation on my original fields? And you see, here, I managed to do all the game generalizing this expression here and putting here some momenta, but I didn't say how they act on my Klein-Gordon field. And probably this is related to your question, how they act on other coordinates, and you will see something fun. Therefore, I am going to ask myself, I put in 3 dimensions And I don't know if I am in the massless case or not. I think so. No, sorry. This is phi. These are my infinite parameters, PR. I am in 3 dimensions, therefore instead of LM, I put my L's. How I do this thing, since phi is has an expansion in terms of A dagger A, this I can write. This is written in terms of A dagger A, and phi is also written in terms of A dagger A. And you can see the following thing, that this is K tilde epsilon L omega L A K of X minus A dagger But still, this is not expressed, but at this point I can try to write this. I can invert, as we explained to students, in the same way that we have on shell, we can express our solution in terms of A and A dagger. I can invert the solution and express my A in terms of phi and P. Therefore, at the end of the day, if I do that, I arrive to the following curious thing that is I wanted to discuss. I do not have a local transformation, but a non-local one. That is what we have. Well, for example, you see this is a non-local transformation because this is an integration of y. And this FL of x minus y results to have this expression here, I dk tilde omega L of k, k0 sine of kx. And it results that you can evaluate this expression here, and what you have is d2k omega lk. I find this rather amusing. That is exponential minus akx plus 3 momenta 1 minus 1 to L divided by 2. And this, therefore, we see that when L is even, this term will cancel, but when L is odd, we'll have something different from 0, and omega L, let me write this expression because maybe you will find amusing. It is omega L of k, before doing the Fourier transform. This is k1 plus ek2 power L divided by k1 squared plus k2 squared all to power L minus 1. Therefore, what we found here, this is, if we pass to the configuration space, this will be something like 1 over the Lambertian square, and up there we'll have derivative of k's to certain powers. Okay? Therefore, to your question, I cannot say that if I do the transformation x to x plus epsilon, I will reproduce this one. And in a way of saying this is that we are getting this non-local expression, and it's appearing this, if you wish, this is a momentum space, the green function of this operator. Therefore, okay, essentially, have more things to say, but I will like to conclude with two messages. One is that there is a pedestrian way of constructing BMS realizations in terms of free field operators. That this realization leaves the vacuum invariant, therefore we don't have shorting, we don't have interaction essentially. And the second message is that, as Strominger was saying in his lectures, by the way, for completely different reasons, it could be that our knowledge of symmetries, saying that we should look for local functionals that are symmetries of a given Lagrangian, maybe that's not general. And here we find a very concrete example that that's the case. We have a non-local expression for the action of this BMS symmetry on our Klein-Gordon field. And that's not a transformation on the basis space. Okay. And maybe I could say as finally that if instead we were able to define an infinite, a field with infinite number of components, XLM, probably in that case we will have ordinary linear representation as we have for the ordinary Poincare group. Maybe I should, even it's 2 or 3 minutes ahead. I prefer maybe to conclude here. Maybe what I would say is the sort of things that I'm thinking, and is the following. In the literature, in the gravitational approach, has been some attempts to construct super BMS. And super BMS, this has been done. There is an old paper that maybe you, Chris, know, of Gary with Awada, I think. I don't know. He constructs some super BMS. It's a very long paper. I don't know how many people has read that paper. But recently, there has been attempts to construct, in the case, for example, of BMS3, how do I put some asymptotics in my supergravity in such a way that I could find a generalization of BMS, and there are some papers on that. But clearly here, you have a natural thing to think that we have not done yet. It is, okay, why we don't consider, for example, in this case will be 3 dimensions, why we don't consider a 3-dimensional free scalar field and free Majorana field that are supersymmetric. I will have the corresponding focus pair representation for this trivial supersymmetry, and I ask myself in the same way that I generalize the corresponding Q, we'll have something that will be some spinor. How can I generalize the spinor? And it's pretty obvious that in the same way that you have the linear equation for the flat spacetime that the square, it gives the Klein-Gordon equation, the square root of what we are doing of this curved space should be the Dirac operator in these hyperbolic things. Therefore, if one has the energies at a time, one maybe would like to see this one. Apart from the fact that maybe there are funny things that one can ask, is it is the relativistic case, the only case where can I have BMS? And to say something that in the past I did with Chris and Gary, we were studying something that was called very special relativity, where appeared the Ising group. I see. Okay, it doesn't matter. It's a theory where you have some particular null direction. The point is that for this theory, you have that the Klein-Gordon, the corresponding, how should I say, the corresponding Klein-Gordon field in this space is the same that the one for the Poincare case. Therefore, this Klein-Gordon field does not make a difference. But we have studied also the formation of that outer. Therefore, in principle, one could say, okay, if we have the deformed sim, can I construct, can I do a construction analogous to that? Can I see if there is a generalization of rho of the corresponding symmetry to an infinite dimensional one or not? Okay, I don't know. Now, yes, now I stop.
Okay.